It is my great honor to be here to present the paper, Surviving in Dark Forest, Towards Evading the Attacks from Front-Running Bots in Application Layer. This work explores how smart contracts evade the attacks from front-running bots. On blockchains, the faster transaction gains profits. Under this interesting phenomenon, front-running attacks is essentially making an attacker's transactions to be confirmed faster than a victim's transaction to gain profits. First, a bot monitors a victim's profitable transaction, like TX1. Then the bot creates its transaction to imitate victim's transaction, like TXA. Next, the bot submits its transaction to faster transmission channel, like private mining pool or high-speed physical network. Finally, bot's transaction will be confirmed faster than victim's transaction, obtaining profit, such like here. When the victim's transaction is confirmed on the blockchain, it is too late and he or she cannot obtain the expected profit that they could have gotten. Therefore, the victim suffers financial losses. Blockchains are susceptible to front-running attacks. For example, the loss caused by front-running attacks on Ethereum reaches more than 600 million USD before September 2022, and nearly 600 million USD from that month to July 2023. As you see, there is a great economic impact. Here comes the research problem. How do Web3 people evade front-running attacks, especially on the application layer that's mastered by people? The answer is important as it evaluates the robustness of current application ecosystem and identifies the areas needing enhancement. Additionally, the answer reveals novel evading strategies in real world, providing guidance for Web3 developers in constructing defenses. However, we have the following challenges. The first one is lacking ground truth. The scope of evading strategies is unknown, which makes it hard to systematically summarize deterministic patterns for detection. And the second one is the high analysis bar. Evading strategies involve complicated contract execution. This is more challenging when the contracts are not open source. To solve challenge one, we refine the research scope based on the attacks from security conferences and smart contract auditors, such as Slomis and BlockSec. We use preset rules to detect known strategies and machine learning to detect unknown ones. To solve challenge two, we adopt dynamic binary analysis to force smart contracts to expose their evading protection and design control data flow, profit delivery analysis to analyze contract behaviors. We also adopt trace slicing to extract code snips for clustering models to learn the semantics of evading strategies. Let's look at this figure. We provide the contract bytecode and historic transactions as input. Then the EV detector will conduct detection first by conducting dynamic binary analysis according to preset rules and output the strategy reports of known patterns as well as unknown patterns. For extracting the strategies hidden in the unknown patterns further, we input the patterns to EV cluster to cluster strategies by learning their semantics. After the manual verification, we can leave new strategies. To refine evasion scope as our research target, we summarize advanced bot attacks model based on academia papers and industrial cases. As you see, a bot executes the transaction of public mempool in its local testnet to observe the transaction execution. If these transactions brings profit to a specified account, then the bot will conduct an advanced analysis, for example, control flow, data flow analysis on the contract C evoked by the transaction to understand how does the account obtain profit. Then the bot will try to construct its contract CA by modifying contract C, such as replacing the profit gainer embedded in the contract Cs, so as to let the CA to deliver the profit to the bot. Finally, CA is deployed to the mainnet and runs the victim's transactions to gain profit. Therefore, we summarize the evasion scope that include preventing the bots from executing each attack steps, preventing the last step. That means the front-running transaction will be the defense on the network layer, which falls outside this work. So we only focus on the application layer defense, such as the strategies to let the bot omit transaction or prevent the bot from analyzing the contract Cs or prevent the bot from modifying contract C. And we summarize 4 evading strategies that include execution split, code obfuscation, access control, and profit control. These strategies will prevent the bots in its different steps individually. Next, I will give a detailed introduction about the strategies. Execution splits the contract execution into multiple dependent transactions, which can disguise a profitable transaction to be a failed transaction and mislead the bot to omit it. For example, the victim submits transaction 1 and transaction 2 to mempool. When transaction 1 is executed before transaction 2, then transaction 2 executions can bring 1.5 WETH to the victim. This means the victim can obtain the profit of 0.5 WETH. However, the bot select transaction 2 from the mempool to execute in its testnet without executing TX1 in advance. Then TX2 will fail, which misleads the bot to regard TX2 as a failed transaction, so let it to omit it. Code obfuscation prevents bots from conducting program analysis on smart contracts, including obfuscating control flow to preventing control flow analysis, which can effectively prevent the analysis relying on this. For example, decompilation. And besides, smart developers also design constructor-based obfuscation. That's hiding the code of gaining profit into contract constructor, such like this. The code in constructor will be only executing once when the contract is deployed and then get dropped. This prevents bots to obtain the profit gaining logic from contract runtime code. As bot need to modify the contract C to bypass the corresponding access control for enabling bots to execute the contracts. Developers can implement various access control strategies to prevent bots modification. For example, hard-coded access control that only allows hard-coded account to execute contracts. And bots needs to locate the account value in the contract bytecode and modify the value to be itself to bypass it. Storage-based access control only allows the account stored in contract storage to execute contracts, which implies bots needs to modify the value in storage to bypass the strategy. Obviously, the second one is more difficult to bypass, right? Similarly, bots also need to modify contract C to bypass corresponding profit control for enabling bots to execute contracts for receiving profits. This means developers can implement various profit control strategies to hinder bots modification. For example, hard-coded profit control that only allows a hard-coded account to receive profits. And bots needs to locate the account value in the bytecode and modify the value to be itself to bypass the strategy. And also, there is argument-based profit controls that only allows argument-specified account to gain profit. And storage-based profit control that only allows storage specified account to gain profit, which implies bots needs to modify the value in storage to bypass the strategy. These are the examples of data log rules that help to derive evading strategies. For example, AC constant ADDR means the hard-coded access control and the verification is conducted in instruction address ADDR. And AC storage ADDR means the storage-based access control, and the verification is conducted in instruction address ADDR. PC constant means hard-coded profit control, and X is the constant profit gainer. PC arguments X means the argument-based profit control, and PC storage means the storage-based profit control. OB memory means the memory-based obfuscation, and JMP is the jump address generated from memory. And OB argument means the argument-based obfuscation. To uncover unknown evading strategies, we design a workflow that combines iterative learning and code clustering. Iterative learning aims to update code embeddings during the clustering process, improving the effectiveness of clustering process. Code clustering is for automatically extracting the code clusters, sharing similar patterns, which implies representative evading strategies. However, the input of the clustering process, that's the code sequences, or more specifically, OP code sequence, cannot be directly used for clustering, as it is long and contains noises. For example, strategy unrelevant OP codes. Therefore, we leverage dynamic analysis to collect the code sequence that triggers evading strategies, which reduces code length. We conduct back-chain analysis and code slicing, starting from the triggering point of strategies to extract the OP codes relevant to triggering the strategies, removing code noises. For example, like this OP codes will be slices to be this code, which is shorter, right? We examine more than 6 million arbitrage transactions and 71 significant attack transactions that evade the front-running attacks on Ethereum and Binance Smart Chain. Our findings uncover 32 refined strategies involving access control, profit control, execution split, and code obfuscation. We uncover 14 access control strategies. They verify transaction caller with constant values, the values from fixed storage slots, mapping values, and the values in a specified offset of the bytecode. We observe authentication, that's comparison operation, not only implemented with equation, but also subtraction and XOR operation. Besides, there are value conversions before the comparison, such as shift left and XOR operation, hinders bots in understanding the authentication logic. Additionally, we also discover there are other authentications that do not target on caller, but on core value. For example, the contract authenticates core values should be equal to a specific value. We uncover 10 profit control strategies. Contracts specify profit gainers with constant arguments, value of fixed storage slots, value of mapping, return value of core, the value in a specified offset of bytecode, and created account. Similar to access control, there are also value conversions on generating the profit gainer, such as XOR and addition operation. This makes bots not easy to understand the profit gainer generation, increasing the difficulty in bypassing strategies. Besides, we also find extra defense for protecting loading profit gainer into EVM memory, such as only when core value is a specific value, the profit gainer can be loaded. We introduced an impactful and interesting attack that leverage execution split strategy to avoid being run by bots. Transaction 93AE is an attack that caused a loss of more than 40,000 USD on Binance Smart Chain. The attack is split into transaction 9308 and 93AE within the same block, 345064117. Specifically, transaction 9308 sets a contract variable to be read by transaction 93AE. If transaction 9308 is not executed before transaction 93AE, then the transaction 93AE will reverse due to a fail rate. As a result, when bots inspect transaction 93AE without firstly executing 9308 on their testnet, they will see a reverted transaction and cannot observe the practical attack. We uncover 7 code obfuscation strategies that prevent bots analysis. Interestingly, some contracts specify jump address by core arguments, memory values, storage values, which effectively prevents control flow analysis. Besides, some contracts only generate jump address when they are executed in mainnet by checking the chain ID. Some contracts only generate a jump address when core value is a specific value. We also observe the attackers in those impactful attack cases like to hide their attack logic in contract constructor instead of runtime code for avoiding being discovered. Here we introduce other interesting findings. For example, we find hard coding solution is more popular in Ethereum. That's using constant value to verify transaction caller or specify profit gainer. But in Binance, storage-based solution is more common. Storage-based solution is more effective in evading bots from running attacks, as this increases the difficulties in bypassing access control and profit control. We also find some developers maintain the bytecodes with a specific layout that's storing crucial values in specific bytecode offsets. If bots modify bytecodes for bypassing the protection, the layout will be destructive. This means the functionality will be invalid, which achieves the code integrity protection. We also find developers prefer using arguments to hide jump addresses, preventing static control flow analysis from bots. This is because jump address cannot be generated without appropriate arguments. To validate the performance of EVScope, we also design a strawman approach as comparison. Strawman employs decompilation and code search to detect evading strategies, while EVScope uses dynamic binary analysis and machine learning. We construct a verification dataset consisting of 400 samples and obtain the results. We find EVScope outperforms strawman significantly, achieving the highest F1 score, which proves the limitation of static analysis in demystifying evading strategies. Here we provide 3 suggestions for evading bots. First, developers are not recommended to expose secret in contract bytecode. For example, the account used for verification, the profit gainer used for specifying receiving profits, because this enables bots for easily obtain the values of legitimate caller or gainer and guide them to replace the corresponding values in bytecode to bypass protection. Second, developers can maintain specific bytecode layout to protect the integrity of the code. For example, storing crucial data like profit gainer in specific offsets and use EVA instructions to load the values from the offsets. When the bot changes the bytecode, they cannot keep the data in the original offset, which leads to the execution failure. This prevents bots to execute the contract after modifying bytecode. Third, developers can design codes to check the runtime environment of smart contracts, such as detecting chain ID, verifying block height, and so on. This prevents bots to execute the contracts in their test environment. Finally, let me conclude the work. We take the first step to demystify evading strategies of real world, assesses their susceptibility and getting bypassed, offer suggestions for enhancing defense. We propose EVScope, the first framework that leverages dynamic binary analysis to live evading strategies. And we uncover 32 interesting strategies. We propose the first evading strategy dataset, which is derived from the analysis from 6 million arbitrage transactions and 71 impactful real-world attacks. Thank you for your listening. If you have any questions, please feel free to mail our authors. You can also access the artifact by this link. Thanks.